All right, hi, I'm Dante.
I'm Lance.
This is our comp sci project we did this term. We created a CSGO AimBot using a convolutional neural network. So first we need to explain what CSGO is. It's basically an online multiplayer first-person shooter game. Basically you control with your keyboard and mouse, and it's like multiple teams of different players like shooting each other, like completing objectives, like planting bombs, defusing bombs, stuff like that. So yeah. And so the aim of the project is we're to use a convolutional neural network to create like we're creating object detection convolutional neural network that detects the players in CSGO. And that's different from image segmentation which is where it has like the full outline. Object detection just has like a box around the object.
And adding on to Dante's explanation, we wanted to make a program, an aimbot that was low visibility to anti-cheat programs. So it would be difficult for CSGO to detect us doing stuff we're not supposed to.
So normally what an aimbot does, it works it directly like intercepts the game packets sent between the server and the game, and it just like directly says, okay, shoot this person. It edits like the game file. So this is what it would look like. You see it just like snapping to all the players, and the player doesn't really have to do anything. You just like kill everyone. But this is very noticeable. So basically, this is what the object detection for a CSGO player would look like. It has you have a box around the head and a box around the body, because we always want to aim for the head when it's visible.
And what's different from a conventional aimbot is when we use machine learning and convolutional neural networks, it's actually, we're not intercepting any game packets. We're not talking directly to the game. So the program kind of acts as a player itself by reading the screen and trying to identify what's on the screen. For instance, we see a box for a player in the head here.
Yeah, and then the program would actually move the mouse like virtually instead of talking to the game directly. So it's less visible to anti-cheat. So yeah, before we started our project, we looked at several similar projects of like aimbots and in video games and using like convolutional neural networks. Yeah. So first we need to explain what is a convolutional neural network. So basically, in our case, we did black and white pictures of the game. So we had you take a picture of the game, and for example, this would be the picture, and you turn that picture into a matrix of values, basically like what color the pixel is. And through that, you have a feature filter, which is like a small area of the picture, and it would go through and scan the entire picture through this, like, for example, here's the 3x3 box in this image. And then from this big matrix, scan through the feature filter, it creates a smaller matrix called the feature map. And basically what the AI does is, for example, if we're like trying to identify a circle, each feature would be like a curve to the right, a curve to the left, curve down to the right, curve down to the left. So it would first identify all of those features, and where the AI comes in is it has to like say like a probability of how much it thinks a certain part of the screen is this feature. And then once it puts those into the feature map, and then the feature map is then like reduced again to a smaller matrix. And then it's turned into a list. So like basically an array, where then there will be a lot of different parameters to decide whether or not that array represents the object that we're looking for.
Yeah. To add on to what Dante said about the circle example. So the smallest feature map we would use would probably be edges. So what Dante said, the curves and the straight lines. And then when we go up a layer, using a second convolutional layer, we can detect higher level features such as circles, because when you put edges together and you do a feature filter on a set of edges, you can find things such as higher level features such as outlines of things. And going up from that, you can find more specific things such as head or body, player, whatever it is. And it's going to be the heads of the players in our case. So it's going from a small to a macro view of the input picture we get.
So yeah, this is the full process. Yeah. And so this is what it would look like for like you can see it identifies like the oranges, the bananas, different things. And this is what we aim to achieve, except with players in CSGO. So I guess in this case, like for the orange, it would detect all of the first broken down into like many small features. It would detect like very small chunks of the edge. And then the next feature map would be like a larger area before eventually turning into the full orange. And same for like a cat, it would be like different parts of the cat. And the good thing about this is, since it's a neural network, even if the cat is like in a different position, like from the side or from the back, different angles. Yeah, as long as you give enough training data with all the cats in different positions, it will detect in all positions, because it doesn't only know like if it has to be like an eye in the top right and an eye in the top left, and then like the body below. It knows it's a cat even if it's like the head is below the body, because it's looking at like the overall shape. Yeah.
Okay, so moving on to how we tackled the problem of creating an aimbot for CSGO. This is our methodology for actually making the aimbot. So we go from image collection, labeling, to processing, then training and testing. So starting with image collection, here's a sample image. This is one that I took in game with a game of bots. So what we see here, we see what the player would normally see when playing CSGO, except there's actually there is a crosshair. So what we see here, we have an enemy. And the goal of the aimbot is to find where the enemy's head or body is and move the mouse there. So our next step will be to label the enemy, basically. So for our project, we use two classes. We use the small box for the head, and then another class for the outline of the player. And by using this website we found called RoboFlow, we were able to easily annotate simply by drawing boxes around the things, and the website will basically spit out the coordinates of where the bounding boxes were on the image, and we can use that to train the data. So after we label our images, we go into image pre-processing. So not every image is equal. We may have images of different sizes, maybe images with different colors, different content in them. So we go through a set of pre-processing steps to firstly reduce some noise and make the image more easy to process. For instance, we change it into a grayscale picture. Doing this reduces the number of color channels from 3 RGB to 1, which is grayscale. So this basically reduces the complexity of the image and makes it easier for the neural network to process. You can see here, these are some of the options we added for pre-processing. The top one corresponds to the image here, and this is the one that we actually use. And then the final step for training is image augmentation. So basically, we can kind of cheat a little bit when training neural networks, especially convolutional neural networks, because data, it's hard to come by, right? It took Ray, Dante, and I a couple, like, I don't know, like 2 weeks to create the data set that we required, and that was only 600 something images.
We have to manually,
exactly. Because
take pictures,
we have to manually label everything. So a way to actually make this process less tedious and make it easier for us to train our neural network was to do something called image augmentation. So what you basically do is you get your data, you transform it in certain ways that makes it into a different set of data and feed it into the neural network to train. Because although they're made from the same source pieces of data, they function effectively as different pieces of data. So the neural network can learn from all three of them. Not all three, but like however many of them. Using RoboFlow's free version, we were able to get 3 images per raw image. So if you look here, there's we have a random rotation between -10 and +10 degrees. So if you see the back image is slightly rotated. Shear, this means like kind of stretching. And yeah, and then we have a brightness filter as well. that makes it brighter or less bright based on random chance. If you see the first image is it's much darker than the back images. So this is a review of our pipeline. We take images, label them, pre-processing, then augmentation. So we were able to go from 647 images to 1,800 images using this process. And another interesting thing that we did was we actually included some images with no players inside. So this helps the neural network know when, like, for instance, if you see like a something that the computer might think is a player, this images like this will actually help the algorithm find out that there's actually no one there. And this is our training process. So if we look here, that's because we're not machine learning experts, right? So we didn't create our own framework for machine learning. Instead, I opted for the very famous and popular YOLO v5 by Ultralytics. So YOLO v5, standing for you only look once, version 5, is a object detector, a two-stage object detector that Ultralytics made. It has some very complicated math that I do not fully understand, so I will not try to explain it. But yeah, so basically we used Ultralytics YOLO v5 network to train a framework to train our data on. And we use weights and biases. This is a website that we use to monitor our training data. So if anything went wrong, we could actually just tell by looking at the graphs and bounding box informations on weights and biases, as you will see in a second. Okay, so this is the accurate training data. If you look at this image, you see the augmentation and pre-processing. It's a little bit brighter than it's supposed to be, and there's a little bit of stretch and crop. So the image looks kind of weird, but that's what it's supposed to be. And this is the labeling of the image. So what RoboFlow does is it takes the bounding boxes that we manually draw, it transforms it into coordinates of the bounding boxes and the classes. So we see here a 0. This means player, and 1 means head. And the 4 numbers corresponds to 2 points on the bounding box of whatever object we're trying to detect. And these are relative coordinates. You see they're between 0 and 1. So they're normalized coordinates on the image. And here we see what training the model actually looks like. This is what the model sees, basically, in essence. If we look at the left image, you see the player. First we see a big blue box. And then the blue box kind of there's a little outline right around the edge of the player. That is a smaller blue box that indicates the true outline of the player that the model was able to find. And if you look at the red boxes, they start at the player, then they converge towards the head. So this is the machine, this is the algorithm iterating itself to find the things we want to find. So if we look at the right here, we have a different image with a lot more bounding boxes, as we can see. But if you actually compare, actually no, yeah,
like the numbers.
Yeah, the numbers indicate the probability of basically the numbers are how much the machine thinks a certain thing relates to a certain class. If we look at these two images, these two are actually the same image. So down here we see one version of the model. This is another version of the model. Here we see a 0.012 probability of a head. That's what the machine thinks. And over there we see a lot more bounding boxes, but actually much lower probabilities. So this model, I would actually say, is better than this because firstly, it's detecting a lot more stuff. It's more versatile. It can react to more different things, and it has a lower accuracy, probability of predicting, like the ground to be a player head. Yeah. So after we trained the model, this is how the aimbot actually runs. These are just the components of the aimbot. It's actually pretty simple, like 600-700 lines of code. So after we start, we have a listener listening for a key press. When you press the / key, the aimbot starts. We predefine an area of the screen for the aimbot to grab. It's usually a 640 by 640 square of pixels in the middle of the screen. Then we convert it to grayscale and store it in a NumPy array. We input it to the neural network, which we import via PyTorch. Then if the network detects something and there's a head detected with a confidence of higher than 0.5, then we move the mouse. Otherwise, loop continues. And this is how the aimbot kind of works.
All right, so this is an example of the testing.
Yeah, so over here, before we start, we have 3 windows here. This is the UI of the aimbot. So basically, this is our little user interface. These yellow buttons you can actually click. So the bottom one cycles the mouse mode. We have 3 modes at the moment. We have snap, which is like kind of a snappy way to move the mouse. We have
That would be easily detectable because the mouse doesn't really like move. It just goes straight to the head.
Yeah, I actually tweaked it a little bit so it does go in intervals,
Oh,
but it's
okay.
it is still kind of
Yeah.
detectable. And then we have 2 other modes. One of them is PyHM. It is a much more human way of moving, but it's still not random enough to the point where I think anti-cheats won't be able to detect it. Then we have another one, which is PyAutoGUI, which is also not the best. We weren't the most successful with the human mouse movement aspect of this. So I'm gonna do this now.
Yeah, so this is the actual game. You can see.
Yeah.
So right now the aimbot has been turned on, and you can see it's snapping to all the players. We can just shoot them.
It does this weird jiggling thing because in the basically in the microseconds where it's detecting and between detections, some of the players actually you either move or the machine starts thinking that it might be something else and it switches the detection between players sometimes. So I wouldn't call it a bug, but it's just how machine learning works. Yeah.
So overall, you can see it's very accurate.
Yeah. Oh, and an additional thing is that we actually didn't program the algorithm to click the mouse for us. I think that may be something we might want to work on in the future, but yeah, just the moving of the mouse is what we wanted to do at this stage.
And here you can see like the actual like bounding boxes.
Yeah.
That it's detecting all the players and like the heads.
I can run again.
Yeah. Do you guys want to see again?
Yes. Oh,
Sure.
okay.
So you see the screen on the right,
Yes,
Yeah.
the red side is what the player sees.
right?
This would be in the background or on the second monitor, and this is what the algorithm sees. It's a box in the middle of the screen.
It doesn't see like the full screen.
Yeah. Because it takes way too long to
Yeah.
process that many pixels. An interesting thing we found is do you remember when we changed the area of the screen from like a wide
Oh, yeah.
section to a square? That immensely improved the accuracy of the model. I'm still looking into why that happens. I suspect that has something to do with the model stretching its, not stretching its feature maps when we input an image that's not the native size. Yeah.
All right, so based on one of the most important aspects of the aimbot is the performance, how fast it can run on a computer. Because if the aimbot is reacting too slow, then it won't be able to shoot the players in time. So ideally we want it to run at like the same frame rate the game is running. So every frame in the actual game, something is moving, the aimbot can like keep up with that. So I guess so we tested on 2 computers, the school laptop and the Lance's gaming PC. So as you can see on the laptop, it didn't do so well. So the game can run fine on the laptop, but the aimbot is only running at around 3 FPS, which isn't really enough to like react quickly. And at the gaming PC, it still didn't run at an ideal frame rate, but it was fast enough to work like you saw in the video just now.
Yeah, and this massive disparity is due to the way machine learning neural networks are processed. So because everything is computed in parallel, there's no dependencies between each neuron in the same layer. You can actually do all the computations for one layer at the same time. That's what parallel computing. Our laptops don't have. This one has.
It's not like multi-core.
Yeah, this one has 6 cores. But on my gaming PC, I have 4,000 graphics cores, CUDA cores, we call them for NVIDIA graphics cards. And that enables us to do much faster parallel processing.
Yeah, and I guess since it's a neural network, there's like millions of parameters
Yeah, we have
that need to be
7.5
calculated for every frame. Yeah, so in conclusion, I think overall our project was a success. We were able to create an aimbot that can aim like accurately and shoot at players with a convolutional neural network. We were not able to create a like very convincing human mouse movement, but I'd say overall it was still a success. And we learned a lot about like managing a project, and also I think I learned a lot about like neural networks, especially. Yeah.
And I think especially working with a non-officially supported language like Python, it's really annoying juggling versions between different developers. For instance, YOLO v5, it actually doesn't run on anything more than Python 3.7. And a lot of it was really annoying to get all the packages to mesh together correctly, basically. And there were loads of other difficulties, but if you're interested, ask ahead. So yeah. And then I think after this we have boring technical stuff if anyone wants to know. But questions?
Ladies and gents.
Wait, so there's over here if you want to see. Oh, that's the actual definition of the network if anyone wants to see it. And there's more boring technical stuff if anyone wants to see more. Matthew?
So in the actual CSGO game, like would this work in the casual player mode or?
It's gonna work. It's just, you might get banned.
banned.
It's gonna work. Yeah.
Because it's faster than a human plays.
Because it's still
It's-
mouse movement still looks like suspect.
It's instantaneous mouse movement. It's like
Okay.
it's not continuous, right? It's like you go from one point directly to another point without the path or like the random human like hand like shakiness. So yeah.
Would you have to code that in, like a timer with a random?
Yes,
timer?
that is actually something I've been thinking about. If we had more time, I probably would have developed my own human mouse movement library, but we didn't get that. So
So what did you use to work together? To
We
coordinate?
used
your efforts?
mainly GitHub.
GitHub?
We had a shared GitHub.
yeah.
And also RoboFlow, we're both on the same RoboFlow project, so we can just, because image collection, that was a big part of it.
Yeah.
So we can both collect images by ourselves and then just upload to the RoboFlow.
I think Ray had a question.
Oh, yeah, I have two questions. So can you talk more about each level of the neural network you use?
Sure.
How do you define one level and how do you define like the difference between one level and the next level?
Can you be more specific? What do you mean the difference between one level and
So
next
like
level?
you're mashing like components in one level together to create a second level.
Right.
Like,
Here.
what is that? Like, can you specify what exactly you're meshing
Okay.
together?
Yeah, sure. That is more hard to understand, so I'll just use this. We input something, an image, as a array of color values, right? So basically, if you see here, this is a fully connected layer. This means that when you think neural network, probably the first image that pops up
Yeah.
is something like this, right? You see how everything is connected? These are called fully connected layers. This is basically what happens in a regular neural network. Then we have hang on.
The difference between like convolutional neural network and neural network is basically like what we talked about at the beginning, the feature filter. In a convolutional neural network, it would basically look at the entire screen with one feature filter, but with the CNN, and it like scans smaller sections of the screen and then turns it into a feature map.
Yeah, and also we use a more, I don't want to call it advanced, but it's a way more efficient way of connecting networks called sparse connections. Sparse, I don't know. Sparse connections. So basically, when connections between neural networks, if you think of it as a big matrix, every layer is a one-dimensional matrix. And when you do the math, it's a massive dot product, basically. The connection between two layers is a dot product between the parameters of each layer, right? when you do the dot product, inevitably some of these values are after you train the neural network, these weights, like the values of the parameters on each level, on each neuron is what's actually being trained. Like the connections is what's actually being trained. When these connections have very small values, that means they contribute little to the neural network, right? If you have something that has input like of 10 million, but it's a weighted sum, right? So wait, let me put. Weighted sum. All right, this. So a weighted sum is how each successive neuron on the next level is calculated. So if you look at the left side, we have one level, and then this output after the unit step function is one neuron on the next level. Every connection is fed into each neuron on the successive layer, right? And some of them will have low contribution. So if you look at the sum, it's the weight times whatever input you get from the previous layer, right? Some of these weights are like very close to zero. So even if you have like 1 million as an input, it's still the value it contributes to the next layer is still relatively low. So by utilizing like a sparse connection, so basically you cut the connection, you just set it to be zero. It makes the network much smaller and easier to pass through. That is the connection piece. And you had a second question, I think?
Yeah, like to my understanding, I think you have a threshold because you calculate like the probability of a head occurring somewhere in the screen based on like the pixels there.
Yes.
Is that threshold being like set manually, or does the computer figure out? the
Yeah, we
threshold?
can change it.
Yeah, we can change the threshold of how low or high we want to go. Right now we have it set it to be 0.5, but we can set it to be lower. But I don't think there's really any use there. The model's quite good actually. We get like we get like 0.9 something, I think, usually when you detect. So there's no need to go lower. If we wanted a faster model with less parameters that would be less accurate, we could potentially lower the confidence value. So maybe make it 0.3 and have a crappier model that basically runs faster, sacrificing some of the accuracy. And that would be one of the uses if you want to change the
That would increase the FPS
Yeah,
in
that
like
would
the
increase-
graph.
But you gotta like cumulatively type in the threshold. It's not like the program goes back and forth and figure out what the right threshold.
I mean, the threshold, it's something you said, right? The threshold actually has nothing to do with the actual network because the network spits a probability, right? It gives out a probability. Whether or not we want to act on that probability has nothing to do with the actual network. So that depends on how accurate you want the model to be. So
Okay, so from a project point of view, what are, we always talk about what's the point of this and everything. So, I mean, what are the main things that you learn?
do you want to go first? Or?
I think this is my first time working with like AI, any like neural network related projects.
Yeah.
So I think I definitely learned a lot. I used to be like very intimidated by it, but after like now like working on this project, I think like after I actually learned about it, I realized it's not as like complex as it seems.
Okay.
Yeah. And also I learned a lot about like working with like a group project in coding, because everything previously, or most of the stuff we've done is like individual.
Right.
Yeah. And for me, as I mentioned before, with the learning to juggle different versions of software, coping with problems that I've never seen before, like what even is that? Like, I don't know. Like, yeah, coping with problems I've never seen before in such a high level of math. Like it's been hard to understand. Like half the time what we're doing, like I understand what we're gonna do, but like the microscopic view of like what's actually happening, it like bugs me sometimes. And like just getting over like not understanding what I'm doing actually has been a big part of what I learned. And learning to use all this different software, learning about RoboFlow, Yellow V5, actually using it, that stuff has been fun. Yeah.
Would you consider taking a course in college?
Yeah, definitely. I applied data science. So.
Oh, okay.
Yeah, I want to work on my own like neural network project now as well. Now that I kind of like know what it's about.
Yeah. Went better. Anybody else?
Yeah, I actually have two questions.
Yeah.
First, do you see like you're gonna release this project into like a public?
That's a good question. In its current iteration, no.
Mhm.
But I've been looking into a method to make the network a lot faster, basically.
Mhm.
Do you remember what I said about sparsely connected networks in response to Ray's question?
Yeah.
So some people have been developing recipes to speed up neural networks, especially for object detection things like real-time things like object detection. So someone actually made some recipes to optimize YOLO v5, but because of the aforementioned juggling of versions and how it's impossible to mesh different versions of software, I could not get the sparsified version of the network to work. So right now we're just working kind of with a stock YOLO v5. And if I could get it to run faster, then I think it would be a possibility to release this into the wild.
And my other question was like, do you have like what are kind of like the pros and cons to using your aimbots, like the aimbots are like kind of existing out there already?
Okay, do you want to take this?
I mean, right now, if I was like an actual like hacker, I feel like there wouldn't be like, I would probably pick a different aimbot than this one if I just wanted to like actually hack in a game and get away with it. Because right now we still don't have the human mouse movement perfect, which is that would be the main advantage of like a neural network aimbot, is the undetectability once the mouse movement is like mimics humans.
Yeah, I think once we are able to get the speed of the network up and integrate proper human mouse movement, it'd be basically undetectable. And if we can run it as fast as, I don't know, like 60 frames per second is long, right? I think even if we can get it to 30, I think that'd be really usable.